It is truly a period of happy days for the semiconductor industry. Just consider that we, as an industry, 2017, we grew 22% this past year after a long period, back almost 20 years at 3% average growth, the last 6 years just under 3, and the last 2 years less than 0.5% growth. And while it was memory dominated, it wasn't all memory dominated. The non-memory part was about an 8.4% growth, so really a good period. It's also good because research and development really soared in 2017, 9.8% growth, although R&D grows most years, still a very big step up. Now, Mark Edelstone, one of the most respected analysts in the industry over the last 3 or 4 years, has been projecting that because we're a mature industry, because we're not growing much anymore, we're going to consolidate. And as he says, there'll be just a few big suppliers supplying the semiconductor industry. But in fact, 2017 suggests that's not what's happening. If you take the announcements, and that was driven by getting to this $100 billion valuation of mergers and acquisitions in the semiconductor industry, and say which of these announcements actually occurred, we find that a lot of them did not, some of them may not, and 2017 was one of the lowest years for mergers and acquisitions in the semiconductor industry in recent history. And the big one is the increase in spending for venture capital. After a period of averaging about just under $400 million per year, we jumped up in 2017. And 2017 alone, $900 million, back at a much higher level for venture capital funding of fabless semiconductor companies. And in fact, if you look at that, what's really interesting is first, second, and third round funding. These are new companies doing new things as opposed to additional funding for established companies. Round 1, 2, and 3, you can see in the blue round 1, notice the highest level in recent history and an incredible $566 million in the second quarter of 2018. We're on a roll. And if you look at what these companies are doing, it's a reflection of what you've heard the last 2 days, basically domain-specific processors and all sorts of other special purpose kinds of chips, everything from Bitcoin mining through deep learning and other special architectures for special applications to overcome the problems we've heard about, particularly in our keynotes from Bill Daley and John Hennessy. It's clearly a new wave of design innovation. If you take a look at them, in this year alone, 2018, 13 fabless semiconductor companies that are have revealed that they're designing AI processors or deep learning processors of one sort or another. And take a look, second quarter total funding, that's beyond just the AI processors, $1 billion in second quarter, remarkable uptick in new ventures. Now, unfortunately, not everything is happy. If we take a look at China investments, we find that it dwarfs anything you've heard about in the last 2 days. The 2014 fund was $20 billion, and the Chinese, I think pretty clever, they simply took the $20 billion and gave it to private equity. Private equity then matched it with another nearly $100 billion, and that money has been pouring in largely into manufacturing, but increasingly into design and other aspects of the semiconductor industry. And look what's coming. Hasn't been announced, but looks like it'll be just under $50 billion additional from the government that will go into making China not only self-sufficient, but it's their hope, a leader in major technologies, and particularly the ones we've been talking about the last 2 days. Well, how about that early round funding that I was celebrating here? Let's take a look at who's doing the investing in all those startups this year. The yellow here is China, and the blue down here is California. And not to offend anyone, but most everything else doesn't really matter. It's all in those two places. And if you do a comparison, the Chinese, in the first 3 rounds of funding, invested 3 times as much in 2018 as the United States did. And the number of fabless companies in China is growing. We went through this long period where the number was about 500 companies. And as time has gone on, just recently in the last couple years, that number has jumped up to around 1,400. And you say, what are those companies doing? Well, they're doing what you expect low-tech companies to do. They're power devices and analog devices and MEMS and things where you don't need to have the latest 7-nanometer technology. But increasingly, looking down here, it's video compression, image processing, things like that. Well, those companies, if you analyze them, and we keep track of all those that are clearly legitimate companies, they have products, they have design tools, a lot of them even pay for them, and if you compare their employment in 2006, just as an example, you take the companies that had 100 to 500 employees of that set in China in 2006, that was 10% of them. If you look at it today, that's now 45% roughly of the total. So they are getting much bigger, and they will have more of an impact. Now, I'm supposed to talk about applications, and predicting future applications is, of course, difficult. One reason is that sometimes technology and the application come together at the same time. Sometimes technology sits on the shelf. One of the big impacts that DARPA had was the emergence of artificial intelligence, which, as I've just shown you, is a major driver today. But if you go back to when DARPA was funding all this, and look, in 1986, the cover of High Technology magazine, you see artificial intelligence. The big boys get in the act, the heavyweights. Does anyone know who this person is? You recognize him? Nobody? That's George Hallmeyer. Yes, he was head of DARPA, late 70s, and had Steve Walker's job. Does anyone recognize the other one? Okay, well, it's all right. So artificial intelligence, 1986, it didn't have that big an impact at that time for a lot of reasons. We had a lack of big data available to analyze. We didn't have an Internet of Things to generate that data. We had very limited computing power, and the computers we had were largely traditional. We did have some Lisp machines, and we needed more advanced algorithms. But really, the biggest thing was it wasn't obvious how you could make money at that. And yet, today, all of those things have either disappeared or are rapidly disappearing, and so AI becomes an application area that almost undoubtedly will be generating opportunities through the decade ahead. Well, if we look at what's the AI impact going to be on the semiconductor industry beyond just the obvious applications, one way to analyze this is to look at Gompertz plots. A guy named Benjamin Gompertz in 1825 proposed a time series modeling for various functions like population growth or the growth of tumors and other things, and was remarkably effective. And the Gompertz formula is what you would think of as an S-curve. It's a double exponential, 3 coefficients, A, B, and C, and then time, and the coefficients determine the shape of that S-curve. So we've looked at Gompertz plots for all of the potential emerging semiconductor applications, and it's interesting that one overwhelms the others in terms of its magnitude. Now, just to show you how the Gompertz plot works, this is just an example, but if you took total cell phone subscribers, that's what the history has been. It's been an S-curve. This is cumulative number of subscribers over time. 2015 is the last year here. Now, if you had taken the data which existed, you can barely see it here, the blue data there. If you went back to 1997, solved for the three coefficients, A, B, and C, and then did a forecast using the Gompertz formula. That's what it would look like. The green line is the Gompertz formula. The yellow line is reality. This thing is very, very accurate. So we've applied it to all sorts of businesses, and one of the things you find is that the server business is going to be healthy for as far out as we can see. It's a growth business. The demand for server capacity is almost unlimited and currently accounts for 4.2% of all semiconductor revenue. Well, server revenue hasn't been growing that fast. It has taken off recently, but the unit price has been coming down as fast as the growth has occurred. But in fact, Gompertz says there will be sustained growth. But the other thing that will happen is these big server centers that we're using for all the enormous compute power we need for artificial intelligence are going to be complemented by increasingly powerful edge node or chip-based solutions. Now, if you look at what the biggest applications are today, the one that stands out above all others is pattern recognition. The ability to process visual data. Your brain spends about half its capacity doing pattern recognition of things you see visually, but it's also the other kinds of pattern recognition. Audio, eventually smell, tastes, all these things are patterns that you've stored in your brain that our computers need to be able to recognize. And on the domain-specific processor side, all sorts of other applications that are crying out for custom processors because, as you saw in the presentations, the next step in performance is not going to come from evolution, it's going to come from domain specificity. Good example, blockchain processing, Bitcoin mining, but all the other blockchain applications like supply chain management and identity authentication and other things. Now, one of the things I find interesting here is the design technology, because that's the business I'm in. But just like AI, which was around for 20 years before or more before it really took off, the design methodology you heard about yesterday from NVIDIA and again today with Bill Daley, moving to high-level synthesis has been sitting on the shelf for a long time. And all of a sudden, these domain-specific processors now are too complex to design any other way. So if you look, you heard yesterday in the Dr. Kalinga's presentation and others that all these people are moving to C++-based source and generating the complex data paths and blocks they need for applications like the computer vision or network computing, cellular image processing, all these things, it's automated. And why are they doing that today? I think there are really two reasons. One, first of all, it's really relatively recent that we had a very precise formal verification methodology that can take untimed C++ and verify the equivalence with the RTL generated. It's only about 5 or 10 years that we could generate RTL that was more efficient, or at least as efficient as hand coding. But the other thing is change in abstraction is hard for designers. Designers are used to writing Verilog or system Verilog, and so they're reluctant to change. So just look at all the publications from the Googles and Facebooks and NVIDIAs and others. You'll see the new design groups are doing their designs using high-level synthesis, a bit self-serving for Mentor, but still a methodology change that I think is quite important. 5G. Obviously an application growth area, not only because it's a new technology, but because it's going to take a while to get the infrastructure in place. So we're talking about something where new applications will be emerging a decade from now as we finally deploy things and they become available for a whole host of applications that are almost unlimited. But the technology itself has some major barriers. It's demanding to the limit in terms of low power, of the throughput, and the most challenging of all is this latency requirement of a millisecond. We have lots of customers who are designing 5G chips. I've talked to them, and one of them commented to me the last time I met with him that it takes more than a millisecond for the signal to get from the point of origin to the server center and back, even if you do no processing. And I asked him, well, gee, that's going to make 1 millisecond latency sort of difficult, don't you think? He said, no, it's okay. I've assigned a team. They're working on it. I said, wow. What are they doing? He says, I've told them that they need to increase the speed of light. So, okay, so moving on here. IoT, hey, great market, but the people that see the greatest promise in IoT today are not the semiconductor manufacturers, it's the information owners who deploy that, which is why we're seeing all the Googles and Facebooks and Amazon doing their own IoT devices. But there is good news ahead, I believe. If you look at history, intelligence flows downhill in the electronics and computer world. So just think about the 1960s. We had big mainframes, and we all worked on dumb terminals. And then in the 70s and 80s, mini computers came along and acted as intermediate processors in that environment, still with dumb terminals. But then in the next decade or so, we saw the emergence of the personal computer, working with dumb peripherals, which became smarter and smarter. Well, if that trend continues, you would expect that the cloud of today, interfacing with smarter and smarter gateways, will ultimately deal with smarter edge nodes, and some people would talk about end nodes. A lot of people today talk about the cloud, the fog, and the mist. The fact is, these are going to be more powerful devices, and it's going to challenge the semiconductor technology because they are going to be multi-technology. You can't have a very useful node if it can't communicate, so a large share of these devices will have analog, digital, RF, MEMS, photonics, other things attached, and of course they have to do N0 kinds of power, and this is a simulation problem that the EDA industry has struggled with for many years with our systems customers. How do you simulate a multi-chip or multi-technology solution like this to get accurate results before you develop the chips? It's a very worthwhile challenge in the years ahead. Sensor fusion. So we're collecting all this sensor data, and in some cases we can process it directly, but the other problem is how do we deal with multiple sources of data? No better place than to look at the automotive industry. 346 companies have announced they will introduce electric cars and light trucks. The 144 companies have announced they have autonomous drive programs. This is an enormous groundswell of design activity, and while I don't think they'll all survive, the great news is they will all buy EDA tools. But to fuse that data, originally, all the sensor designers were trying to make their sensors more intelligent and do more local processing. The problem in a car is that you need raw data, because otherwise, as the number of sensors grow, as you move to level 4 and level 5 full autonomous drive, you now have all these software stacks in front of each sensor, and if you take process data, then you can't overlay the data from the radar against the LiDAR, against the visual sensor, and so on. It has to be processed centrally. You have to be able to compare it, which means you fix the latency problem of getting the data together. You fuse it with a single software stack so that you can process it and, in fact, then make sense of it for the application in the milliseconds you have to respond. Security. A really severe problem, really significant, and a particular problem for the Department of Defense. There are some who suspect that as much as 30% of the distribution-based parts could be counterfeit. They come from disposing of computer equipment, which gets taken offshore, and people get the devices and clean them up and resell them, or it comes from reject bins or other sources, but counterfeiting is an enormous problem. safety. You've seen the hacking of the Jeeps getting on the CAN bus and other things, but if you can come in through the chips, it's much more serious than today, where we worry about the operating system, the application software. There's bank fraud, there are all the requirements that are going to come, and DARPA's been a leader. The SHIELD program, in fact, is one clear method that can provide identity. But the problem today is that none of the customers of the semiconductor companies are anxious to pay for the additional security. So if you come in and say, I have an anti-Trojan capability in the chip, they will say, but your chip costs 3 cents more than the other chip. My customers aren't complaining, so very hard to sell. I can tell you the EDA industry has tools to solve these problems. We've had, for years, the DoD applications have required them, but the market isn't driving it yet, and the unfortunate part is that eventually there will be a disaster and people will wake up and then they will demand it. System emulation. If you were here on Monday in the morning, you saw some of the demonstrations and the discussions on system emulation. This one's particularly interesting to me because unlike most of you, when I started in the design world, before we had SPICE, we built emulators out of TTL. That's how we verified chips. And the world evolved. We had commercial emulators, and for a long time, the emulators lagged behind the technology so that the largest of chips could barely fit in an emulator. But what's happened in recent history, well, actually, in the 2G generation of cell phones, everybody emulated the whole system, RF in, analog, speech out. They even put the emulators in vans and drove them around to look at the effect of reflections off buildings. But that was the last generation for doing that. And so the emulators struggled to keep up. Now the emulators are ahead. Now you can do whole system verification, but still most of them that are being used, people are using the capacity so they can have multiple designs on the same emulator and people working, sharing the emulator. What you haven't seen yet, although it's occurring, is verifying the whole system. And this one is a dream of DoD, to be able to simulate not only the electrical, but the mechanical and thermal and other aspects of an airplane. But the automotive industry is anxiously moving ahead. And in fact, this is a real platform. You can actually buy one if you have some money. The stimulus is generated virtually. You can simulate, or you can generate a stimulus for fog or rain or sun or curbs or trees, whatever. And the algorithms are processed in an emulator, so you can play with your algorithms, and it's connected to models that exist for the brakes and the transmission and all that, and do the development. And in fact, for autonomous drive, it's absolutely critical, because you would have to drive a car over 8 billion miles if you were going to do the verification for all the things that can happen with autonomous drive. If you could even do that, it would take 500 cars at 60 miles per hour for 50 years to do it by traditional means, or you'd have to do hardware in the loop. But the other thing is, it's very expensive to get people who are willing to run in front of cars to see if they stop. And so it's going to have to be virtual. And in fact, these systems work. You see on the left, the sensor generates the visual output, then the virtual stimulus generates what the output would be from the sensors, and then that gets processed in the emulator, and here you see it identifying traffic lights and cars and other things, and communicating with actuators to the brakes and so on. And this is how people are already debugging their automotive electronics. Lastly, I'd like to touch on memory technology. Not an application in itself, but a very important driver. Go back to 1990. If you count just the chips, don't worry about embedded memory, just the chips, then 45% of all transistors shipped in 1990 were memory transistors. Today, more than 99.7% are memory transistors. That's a big change. Well, think about the semiconductor learning curve. Now, you've heard about Moore's law coming to an end, and that is indeed true, But very few people talk about the fact that Moore's law is just a special case of the learning curve when all of the cost reduction is done by shrinking feature sizes and growing wafer diameters. Of course, a learning curve has the logarithm of the cumulative number of transistors you've ever produced on the horizontal axis, and the vertical axis is the log of the cost per transistor or the revenue per transistor. And the only reason that Moore's law has been a straight line is because we grow the number of transistors exponentially, so the Moore's law horizontal axis and the learning curve line up. So we've had this long period where Moore's law was a straight line. But we're not growing it exponentially anymore. So we don't have a roadmap from Moore's law, but we do have a roadmap from the learning curve. It will always be a straight line, and it tells us where we need to be in the years ahead. But the reason I bring it up is because a strange thing is going on with the learning curve. If you break the learning curve into memory versus non-memory, you find that the cost reduction in cost per transistor is being dominated by memory, in particular flash memory. So memory is coming down 39% per year per transistor, and the rest of semiconductor, 21%. Well, that's a problem because eventually we're going to have to do something about this on the logic side, but also how long can you go with memory pulling all the weight of the industry? You know you have to stay on the learning curve. Here's the total learning curve, but here's what the DRAM flash learning curve is, and you can see the total learning curve is coming down 37%, DRAM and flash coming down 39%, so really dominating. And one of the reasons is because NAND flash doesn't have to obey the same restrictions. We've gone from 1 to 2 to 3 bits per cell. We grow vertically, but we can see the limits at something like 128 layers in terms of NAND flash. So there needs to be a solution. Well, how would you predict the solution? Once again, I turn to Mr. Gompertz and say, okay, let's look at the number of transistors we've shipped throughout our history. What's the S-curve look like? Here we are. We have shipped a tiny fraction of the transistors we're going to ship even in the next 10 years. However, here we are today, and as you get up here, the growth rate slows unless you get a new transistor or do something very different. So the presentations you heard about alternative technologies, pay attention, because sometime in the next 10 years, at least if you follow the Gompertz plot, you're going to need something that is unlike the current transistor structure. But the other thing you can do is make better use of the transistors you have, and that comes back to the neuromorphic computing we've been talking about, and the fact that your brain does so much better job, particularly in energy efficiency. You can recognize something in a fraction of the cycles that it takes a digital computer, and as a result, your brain doesn't dissipate as much power, and it's able to do things that computers just can't do. Well, for memory, we are very close to the same capacity in semiconductor memory as brain effective bit capacity, and the hierarchical memory, which we need to be more like the brain, probably doable, but nobody has a clue yet for how to do things like invariant memory, where I look at a small portion of your face in a shadow, and I'm able to tell who you are, or I listen to a millisecond of conversation on the phone and I recognize your voice. Your brain has ways of doing those extrapolations that our computers don't have. And on the processor side, you heard a lot about extracting parallelism, a little about error tolerance, but the integration of logic with memory and the continuous feedback, we're still a long way away. So, who is going to create and support all these applications? A little disturbing data here. So take a look. This is the first university degree in engineering and science, and this line you see here is China. And you can see where China is in terms of turning out new graduates, an enormous resource. Now, probably the most fulfilling role I've had in, I guess, volunteer service in the industry has been as a board member of the Semiconductor Research Corporation, where in fact we've managed to maintain and feed that infrastructure, but I have to get worried when I look at the number of engineers here versus in China. And this is the earned doctoral degrees. It used to be that the US educated those from Asia as well as the US, and we still do. But take a look at how much China has moved up. This is all of Europe, but the US is only about double China right now. And if we look at, for example, citations index, who's publishing and where is it being cited, we have Europe, we have the US, but China is not that far behind. They are moving ahead, so it's worth watching when we consider the tens of billions of dollars they are investing compared to a relatively small amount the US government is investing, a not so small amount that industry is investing today. So, to summarize, we have seen a big uptick in the acceleration of the growth of the industry and the rebirth of fabless semiconductor industry to do domain-specific kinds of applications. We have plenty of application opportunities, some of which are solvable in the near term, some will take longer. Memory technology is very core to all of this, and so it's important, it drives so much of it, that we recognize that in the next 10 years there has to be some significant innovation. And lastly, growing and training the developers of semiconductor technology and design is critical to our future growth and our ability to compete worldwide and maintain the leadership you all have developed. Thank you.
Great job, Wally. The thing about Wally is you can't talk about legend or rumor, right? There's actual data behind your analysis, so I love it. It's great level setting. Even if the data looks a little scary occasionally, I think it's great to actually just stare it in the face and look at the challenges that we face as a country. So any advice you're going to give to the community tasked with inventing beyond punching above its weight?
You know, we could work harder and faster, but the bigger thing is we have to work smarter and we have to pick the right problems, because you're never going to equalize that balance of funding, so we have to do a lot more with what we get.
All right. Thank you.
Thanks.
Thanks, Wally.